Welcome back to our session. We're still discussing the formation of salts. We're looking at different reactions in terms of using acids and bases in real life. So we want to focus on, a case whereby you are given a salt and then one needs to work backwards to try and determine, for example, which acid or which metal oxide, which base, which alkali actually reacted with an acid to form a certain type of salt. So it's instead of us starting with the reactants. Now we want to try and be flexible and work backwards to say, okay, if this is a salt that is given to us, how exactly do we, identify the type of acid or the other reactant to give us that specific type of salt, right? Right, okay, so given the following salt, okay, identify the acid and the base required for the preparation and write a balanced equation of reaction. So balancing of equation will be a very critical skill that we would need. Now, in this case, we've got potassium chloride. Now, where do we start? We are given the chemical name of the salt, right? But then we want to come up with a balanced equation of reaction that shows us how exactly this salt is formed. Now, the starting point, our point of takeoff is actually to write the correct chemical formula for the salt. Okay, potassium chloride, the potassium cation, we know it's K plus, right? So we're going back to chemical formula, and then the chloride ion is Cl minus, right? So the chemical formula of potassium chloride as the salt then becomes KCl, right? So we want an equation of reaction that's balanced, that will show the production or the process of getting or obtaining this salt. So we are talking about an acid. Now we want an acid that will have a chloride, okay? So immediately we are thinking HCl, okay? What is HCl? Yes, this is hydrochloric acid, which is typically a strong acid, plus a base that has got which metal? Potassium. So the base that has got, potassium atoms will be, for argument's sake, potassium hydroxide, okay? Because potassium is a group 1, metal, which is an alkali metal. The hydroxide of group 1 metals are actually strong, bases. So these are the the reactants that we actually require. Now, what does this give us? It gives us our KCl, which is our salt, okay, plus our byproduct, which is water, right? Now, the other part that's also important is the balancing. The stoichiometric ratio in which these react with each other is 1:1. So this is actually the balanced equation of reaction for the formation of our potassium chloride, right? Okay, let's look at another one. Now we've got sodium nitrate, right? Where do we start? Once again, we start with the chemical formula. Sodium, group 1, Na plus, okay? Then the nitrate ion, which is a polyatomic ion, NO3 minus. Then from this, we are able to determine the correct chemical formula of our salt, which is NaNO3, right? So this is our salt that we want, right? So what is it that we need? We need an acid and a base that's going to give us that. So the moment we see nitrate, that's where we think about the acid. So the acid that contains that nitrate is actually nitric acid. Now again, chemical formula, nitric acid HNO3, okay? Yes, right? Which is a strong acid, plus a base that contains, a nitrate, okay, sodium, because the salt is sodium nitrate. So this is the formula of the salt. This is what actually guides us, right? So what do we have here? We've got sodium hydroxide, right? So we get sodium hydroxide, which is our strong base, right? Just like potassium hydroxide, because it is in group 1. What do we get? We get sodium nitrate, right? Okay, that's our salt, plus our byproduct, which is H2O, right? So that's our equation of reaction. And if you look at it, it is actually balanced. The stoichiometric ratio in which they react, it's 1:1. Right, let's look at the next one. Now we're also given sodium ethanoid, right? First of all, we want the correct formula of sodium ethanoid. So sodium ethanoid, CH3COONA. Okay, now this is an exception. Okay, I think the unwritten rule in terms of chemical formula, we always started with the cation followed by the anion. So the cation becomes our positive ion, then the anion becomes our negative. Because this, and you can think of it, you know, the salt comes from an organic acid, which is a hydrocarbon, but it's an exception. In this case, we'll start with the negative and then end with the positive cation. So that's why we are there. So we definitely need some acid that contains the ethanoid ion, okay? So the ethanoid ion, CH3, COO minus, and then the sodium, we've seen it before, Na plus. So then we'll definitely need ethanoic acid, CH3, which is a weak acid, COOH, okay? Weak acid, it says to us that it ionizes partially to give us a low concentration of the hydronium ions in solution, and the pH value is closer to 7, but less than 7, okay? Right, so this we react with sodium hydroxide for argument's sake, okay? Right, what do we get? We get sodium ethanoid, CH3, COO, right? That's our salt, right? Plus H2O. All right, so that's our equation of reaction. And again, we don't need to tamper with anything. This is a balanced equation of reaction, right? We also have another one. This one is very interesting. It's copper 2 chloride, right? The 2 in Roman figures suggest something about, you know, the oxidation number, or the charge of this transition metal copper. It means we've got copper 2 plus, and then also we've got the chloride, which is the halide, right? Okay, group 7 elements, okay? Now, if we want to get that, we can think of, you know, a reaction between, you know, an acid and a metal oxide. So what do we know? We know that an acid plus a metal oxide, right, actually gives us a salt and water, right, as one of the alternative ways of preparing a salt, okay? Right, so the acid here must contain the chloride, right? And then the metal oxide must contain copper, okay? So if we think of an acid that contains the chloride ion, it becomes HCl, which is hydrochloric acid, a strong acid, right, plus copper oxide, right? Take note of the formula of copper oxide. Copper is Cu2 plus, okay? And then oxygen is O2 minus. So if you go back to our chemical formula, we would obviously, you get the formula CuO, right? So this is our salt, right? What do we get there? This is a metal oxide. In most cases, it exists as a solid at room temperature, right? So what are we going to get? We'll get copper chloride, copper 2 chloride, okay? Which is CuCl2. That's our salt, plus water, which is our byproduct, right? And then when it comes to the balancing, the copper chloride, you know, formula unit has got 2 chloride ions. Then atoms, then we can put 2 there, so that at the end of the day, the equation of reaction is balanced. So the stoichiometric ratio in which they react is 2:1. This is going to be very important in terms of determining the purity of the salt that we actually obtain from this reaction, right? Okay, now, the long and short of it is that at the end of the day, we appreciate that there are different ways in which we can actually, you know, use in terms of reactions to obtain very useful salts, because our discussion is about uses of acids and bases in the production of salts. Right, so what are we saying at the end? In summary, we are saying that acid-base reactions are used in titrations. These are your typical neutralization reactions, right? And also we are saying that indicators are chemical substances that change color when the concentration of the hydronium ions changes to show the end point of a titration. And the concentration of hydronium ions actually has a lot to do with the pH of a solution. Right. Speaking of pH, we are saying that, when you react a sample of a strong acid and a strong base, for argument's sake, what happens is when that acid-base reaction or neutralization reaction does take place, we need to get some indication at some point as we continue titrating, adding this other solution so that the reaction takes place in the vessel. We need to get an indication of saying, okay, we have reached a point where there is a neutral solution, okay, in terms of quantity of base that has reacted with the acid. So the indicator essentially serves that role. So it gives us, an indication, as the name suggests, of whether neutralization has occurred in a typical, acid-base type of a reaction. And also, we're talking about the end point of a titration. Okay, this is actually when the reaction has taken place, and then we know that equal volumes of the acid, equal amounts of acid and base have actually reacted. So the indicator serves that purpose, in a titration, which is a technique which is based on the acid-base reaction. Right. Furthermore, what are we saying? We are saying that acid-base reactions are used for salt preparations. Okay, so beyond generalizing that if you react an acid and a base, you get salt and water, our focus now will be on the importance or the applications of these salts, in everyday life. So what we're trying to do is that from the theory that we learn in class, we need to understand its relevance in terms of application. It could be in industry. We've also mentioned the fact that, these salts have got, real life and, practical applications, which is why it's so very important for us to actually understand these reactions, in terms of preparation of salts. Right, so this is very, very important. Right, so in a nutshell, we are saying that the types of reaction that gives us salt, we can vary these different types of reaction. So we're trying to locate this section, in our broader chemical change. Right, so that's as far as, the discussion in as far as the uses of acid-base reaction in terms of preparing salts. So you need to, familiarize yourself by way of practice, so you need to practice more and more of these problems so that we become comfortable. With that said, we shall call it a day for now.